All right, in section 6.3, we want to talk about directed graphs and various definitions of things associated with directed graphs. Now, we've already talked about directed graphs a little bit when talking about relations, but we're going to just do a little bit more formal treatment of the subject. So, a directed graph formally consists of a pair of two sets. V is a set of vertices, E is a set of directed edges, and so because the edges are directed, the order matters, and therefore the set of edges will come from the Cartesian product of V crossed with V. So an edge UV, the order matters. U is the sort of the start point and V is the ending point, and it will be pictured as an arrow starting at U and ending at V. Okay, so U is called the tail, V is called the head. So if you think about vectors, this is very similar to a vector. So if you think about the edge of being like kind of a vector, that's the head of the vector, the tail of the vector. The terminology is the same. And then we've seen examples of where the head and the tail are the same, like when we have a reflexive property in a relation, but that's called a self loop. So we have, you know, a vertex, and then the tail comes out and the head comes back into the same. That's called a self loop. Okay. Then we also want to look at the in degree of a vertex and the out degree of a vertex. Okay, so the in degree is the number of edges pointing into it. Essentially, we'll look at the number of heads that are at A, or the number of arrows coming in. And then the out degree is the number of edges pointing out of it. So we would look at the number of edges that have a flat side or no arrow coming out of it. So let's look really quickly at this example graph. If we look at vertex A, the in degree would be the number of arrows coming into it. Now, if you look at all of the edges, there's only edges going out. So the in degree is 0. And then the out degree, well, there's 1, 2, 3, 4 edges going out. If we look at B, there's 1 arrow coming in, so its in degree is 1. And there's 1 going out, so the out degree is 1. If we look at C, there's 1 coming in here, and there are 2 going out. If we look at D, there are 3 coming in, and there's 1 going out. And E has 3 coming in, and absolutely nothing going out. Okay, so sometimes we have an in degree of 0, sometimes we have an out degree of 0, or if anywhere in between. So we already know that a digraph can be used to picture a relation. It's basically like an arrow diagram for functions, but because when we have a relation that has just one domain, then we can use an digraph to picture the relation. Okay, but that's not the only application of digraphs. There's many, many other applications in computer science. For example, in networking, we can look at the communication paths between networks. So like the various vertices represent processors in a network or computers in a network, and the communication path between the computers would be represented by the edges there. We also can use digraphs to look at dependencies in a large computation. So let's say you're trying to parallelize something and break it up into smaller problems so that different computers can work on parts of that problem independently and then take the solutions to the smaller problems and put them back together to solve a larger problem. Well, often there's dependencies. So like this, like I can break up the problem, but I have to have the solution to this part before I can go on to the next part. And so we can represent those kind of dependencies between tasks in a large computation system. Also, we can look at like a social network, and we can look at the relationships between the users in a social network, where the people or the users would be represented by the vertices and the relationships would be the edges. There's lots and lots of other applications as well, but those are just a few. Okay, well, and then in various contexts, these different concepts will come up that we're going to look at in the next few slides. So first of all, we're going to look at a walk in a digraph. So a walk from one vertex v0 to another vertex v1. In a digraph, G is just a sequence of alternating vertices and edges that starts and ends with a vertex. So the first has to be vertex, the last has to be vertex, but other than that it goes vertex, edge, vertex, edge, vertex, edge, and starts and ends with a vertex. And then each edge in the sequence has to appear after its tail and before its head. So that's a lot of words. Let's just look at an example. So let's say that I wanted to take a walk from vertex 1 to, let's say, vertex 5 in this graph. So I could start at vertex 1. Okay, so that's a vertex. And next I would have to go over an edge. So let's say I go over edge 1, 3. So that would be next. And now I'm at vertex 3. And then I could go from vertex 3 to vertex 2 over edge 3, 2. So this is an edge, this is a vertex, this is an edge. Okay, now I'm at vertex 2. And then I could go over the edge 2, 5. And now I'm at vertex 5. It's a vertex. Okay. So this is an example of a walk. Okay, so notice the alternating sequence that goes vertex, edge, vertex, edge, vertex, edge, vertex. It starts with a vertex, it ends with a vertex. And then every edge appears right after its tail. So edge 1, 3 appears directly after its tail, 1, and directly before its head, 3. Okay. Now, when you look at that, you probably say, well, there's a lot of extra repeated information in there that we don't really need. So since the edges are completely determined by the vertex, so if I have vertex 1 and vertex 3, of course the only way I have to have edge 1, 3 between there. So often we don't write out all of this, we just write the vertices. So we would just write 1, and then 3, and then 2, and then 5. Okay, so it implied by this that to get from 1 to 3, I would go over the edge 1, 3. To get from vertex 3 to vertex 2, I would go over the edge 3, 2. Okay, so it's much shorter if I just list the vertices. And so the length of a walk is the number of edges in the walk. So in our example where we had 1, 3, 2, 5, let me write that out again. So 1, 3, 2, 5. Okay, now when you look at that, you see 1, 2, 3, 4. Okay, but it's the number of edges. So if I went from 1 to 3 here, and then from 3 to 2 here, and then from 2 to 5 here, notice that is only 3 edges. So it will be sort of, if you like look at this, you can count it as like 1, 2, 3. You know, the number of. So this is length 3. So it's not the number of vertices, it is the number of edges. Okay. Then we have this walk. So in an open walk, the first and last vertices are not the same. So this one that we looked at, this is an example of an open walk. Okay, the first vertex is 1, the last vertex is 5. Those are not the same. We could also look at a closed walk. And on a closed walk, the first and last vertex are the same. So we start and stop at the last place. So let's say we could start the same way. So we could go from 1 to 3 to 2 to 5. And then maybe we could move on to 4. And then to 6, and then to 2, and then finally end up back at 1. So let me highlight that for you. So here we start at 1 and go to 3. From 3 we go to 2, starting out just like last time, 2 to 5, but we're going to keep going. From 5 we go over to 4, 4 to 6, 6 to 2, and then we end up back at 1. So notice we start and stop at the same place. So this would be a closed walk. And if we were to look at the length of it, okay, once again, we can just count 1, 2, 3, 4, 5, 6, 7. So this is of length 7. Okay, you could also count the number of vertices and subtract 1. So 1, 2, 3, 4, 5, 6, 7, 8 minus 1 is 7. Okay. Now, the next, so we would differentiate now between various kinds of open walks and closed walks. So we'll look at trails, circuits, paths, and cycles. So a trail is a walk in which no edge occurs more than once. So you can't repeat any edges. And we have an example of a trail where no edge occurs more than once. We could do back in this one back here. Okay, I'll go back and highlight it in a second, but we could start off just like we did on this one, but maybe just stop at 2. So if we did this 1, 3, 2, 5, 4, 6, 2. Okay, so looking at that one, okay, so we went 1 to 3 to 2 to 5 to 4 to 6 to 2. Okay, so we never repeated any edges. They're all distinct edges. Okay, so once again, this trail, this is where we have no repeated edges. Okay, then a path is a walk in which no vertex occurs more than once. So notice here we have the vertex 2 showing up twice. Okay, so this one is not a path because we have repeated vertices. Okay, that's the difference between a trail and a path. So a trail, we just can't repeat any edges, and we haven't, even though some of the vertices are the same. And a path, we're not going to repeat any of the vertices. Okay, so let's look at an example from that one. Okay, so let's see if we wanted to try to get a kind of long path where we don't repeat any vertices. Suppose we could start at 1 here and then move to 3 and then over to 2 and then let's say down to 5 and then over to 4 and then over to 6. And at that point, you know, we've gone through all the vertices and we can't like go anywhere else, because if we do, we'll repeat a vertex. So from 6, you know, there are ways to get back to 2 or out to 5, but we would then repeat a 2 or a 5 and it won't be a path anymore. So that's basically the longest path that we can get. So we've gone and repeated no vertices at all. Okay, and then next we have a circuit, which is a closed trail. So that means that no edges are repeated, no edges occur more than once. It's a trail, but it starts and ends at the same vertex. Okay, so for us, our example would be like this one, but then going back from 2 to 1 at the end. Okay, so 1, 3, 2, 5, 4, 6, 2, 1, back to 1. So it starts and ends at the same vertex. That makes it closed, and it's a trail because we never repeat any edges. Okay, and then a cycle is a circuit of length at least 1. So it's going to be closed, and then no vertex occurs more than once. Okay, so no repeated vertices. You might say, well, why don't we just call that a closed path? Well, the problem is that a path, you know, can't really be closed, because closed means that a vertex occurs more than once because it starts and stops at the same one. So it's kind of a lot. You can kind of think of it that way. So it's like a closed path where the only repeat we allow is the first and last vertex. Okay, so it's not really a path because there's a repeat, but you can kind of think of it in that same family. Okay, so there we're going to start and stop at the same vertex, and we will have no repeated vertices. So if we were to look at our example, like this graph back here. I guess there's a simple one here that goes from 1 to 3 to 2 and back to 1. Okay, so the only vertex that is repeated is the first and last one, the starting point and the stopping point. I guess we could get like a longer one, like let's say if we started at 3. So we could go from 3 to 2 up to 1, maybe down to 4, and then back to 3. So this kind of thing. So we start and stop at vertex 3, and we never repeat any vertex other than the first and last. Okay, now once again, these would be, the length of these would be based on the number of edges. So this would be a cycle of length 1, 2, 3. This would be a cycle of length 1, 2, 3, 4. Okay. All right, so let's wrap up with looking at some examples. Let's say we wanted to find a trail of length 8 that's vertex 4. Okay, so let's see. We could start here at vertex 5, and we want to end at vertex 4. Okay, so let's see. We're probably going to have to repeat some, so we could go out here, go 1, 2, 3, 4, let's see then, 5, 6, 7, 8. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8. So there's our trail of length 8. If we had to write it out, we started at vertex 5, and then we went to 4, then back to 5, then over to 6, to 7, to 4, to 3, to 2, and back to 4. Okay, so notice that none of the edges were repeated, so that's the important thing for a trail. We have no repeated edges. So you can see I've highlighted there, we have 8 distinct edges, none of them are repeated. It starts at vertex 5 and ends at vertex 4. Okay, then in the next one we want to find a path of length 6 from vertex 1 to vertex 2. Remember, a path has no repeated vertices. Okay, so we're going to start at vertex 1, and we want to end at 2, and we have to go over 6 different edges to get there. So let's see, 1, 2, 3, 4, 5, 6. So that's 1, 2, 3, 4, 5, 6. Okay, so if we were to write that out, we start at vertex 1. Then we go to vertex 5, to vertex 6, to vertex 7, over to 4, 3, and back to 2. Okay. So that is a path. There are no repeated vertices. Oops, I think I wrote this wrong. This was supposed to be a 4. Because when I looked there, there was a repeated vertex. It shouldn't be. Okay, so 1, 5, 6, 7, 4, 3, 2. Okay. I think I was looking at the number 5. Sorry about that. Okay, and then the next one, we want to find a circuit of length 7. So a circuit, recall, a circuit is a closed trail. And so that's going to be no repeated edges. Okay, so this is going to be no repeated edges again. And also it's closed, so it has to start and stop at the same vertex. Okay, so we're going to start at vertex 3. Okay. So from vertex 3, we could go here, that would be 1, and then 2, and then 3, and then 4, and then 5, and then 6, and back here would be 7. So that's 1, 2, 3, 4, 5, 6, 7 different edges. Okay, so there you stop and start at 3. So if we were to write that out, that would be 3 to 2 to 4 to 5 to 6 to 7 to 4 and back to 3. Okay, so that's 7 distinct edges, and we did not repeat any edges. We did repeat a vertex, but that's fine. This is not a cycle, this is a circuit. And then on the next one, we want to find a cycle. In a cycle, this is going to be no repeated vertices except for the first and last. Which of course have to be repeated for us to get all the way around. Okay, so we want to start at 4. Again, find a cycle of length 5. So I guess we could go here, 1, and then from 5 to 6, that would be 2, and then up here, that would be 3, 4, and back would be our 5th edge. So that's 1, 2, 3, 4, 5 different distinct edges. Okay, the only repeated vertex is 4, the starting and stopping position. So we went from 4 to 5 to 6 to 3 to 2 and back to 4. So nothing in the middle is repeated. The only thing that's repeated is the first and last. Okay. All right, so in solving various problems involving digraphs, these concepts of paths and trails and walks and cycles and circuits will come up an awful lot, and so it's good to know all of those definitions.